There are lots of applications that you can do with linear equations and linear functions. Two of the common ones are percentages and distance problems, and so we're going to do a couple of those here. There are different ways to conceptualize percentages, but one that is particularly useful is the notion that the whole times the percent is equal to the part. Using this format, you can often take verbal descriptions and translate them directly into algebraic equations that you can solve. For instance, in this first sentence, we can actually take each word and translate it into its mathematical equivalent. The first word is what. That is the thing that we are looking for. We don't know what it is, so let's give it a variable name, x. Then we have is. In mathematics, is means equal to 22%. Now, when we write this numerically, we write the decimal version of 22%, which is 0.22. Of usually means multiplication. That's what it means in this case. 430. So a quick multiplication will tell you that 0.22 times 430 is 94.6. And so there we go. The thing we're looking for is 94.6. 22% of 430 is 94.6. We can do the same thing with our second question here. 48 is what percent of 60? Again, we'll go one word at a time. 48 is what percent, so in this case it's the percentage that we're looking for. We'll give that a variable name for the moment, p, of means multiply, 60. So we have 48 equals p times 60, and this is a very easy equation to solve. 48 equals 60p. Divide both sides by 60. We get p equals 48 divided by 60, which in decimal is 0.8. Now, when we report our answer, they want it in percentage form, and so we take our 0.8 and we turn that into the percentage form, which is 80%. So we conclude that 48 is 80% of 60. Now let's do an application. So we're told here that Frank's utility bill this month was $287, which represents a decrease of 18% from last month's bill. And now we would like to know, how much did he pay last month? Let's start by making a variable to represent the thing that we're looking for, right? The thing we're looking for was last month's utility bill, so we can say x equals last month bill. Now let's see what we can make of the percentage. In problems like this, it's often easier to take a statement about a loss or a decrease and convert it into a statement about what remains. So, for instance, if we have 18% of our bill is gone, well, that means that 82% of the bill must remain from the previous month. So now we can restate the problem to say that 82% of last month bill is $287. This translates very nicely into an algebraic equation. 82%, 0.82, of means multiply. Last month's bill, we're calling x, is equal to 287. So we have 0.82x equals 287. And now we solve for x. We can divide both sides by 0.82. And what we end up with is x equals 287 divided by 0.82 is 350. So what this tells us is that last month's bill was $350. And now for something completely different. We're told in this problem that Alice and Bob walk in opposite directions for 10 seconds. Bob walks 2 feet per second faster than Alice, and at the end of their 10 seconds, they are 80 feet apart. How fast was each of them walking? As with any word problem, it's important to start by getting a handle on what it is they're asking us to find. In this case, they want us to know how fast was each person walking. And so what we can do is make up a variable to represent the thing we're trying to find. Now, in this case, we can say x could be Alice's speed, and what we can notice is that there's a relationship between Alice's speed and Bob's speed. Bob walks 2 feet per second faster than Alice, and so if x is Alice's speed, then Bob's speed we can express as x plus 2 feet per second faster. Now let's draw a picture of the situation. Alice and Bob started from the same spot and then walked in opposite directions, but one of them walked faster and so went further. Here, this would be Bob's distance, and here, this would be Alice's distance. We also know that the total distance between them when they were done walking is 80 feet, and so after they were done walking, the entire distance here is 80. So if we could come up with an expression for Bob's distance and Alice's distance, we can relate it to the 80 up here. Well, that's where the distance formula is going to come in. Distance equals rate times time. Let's start with Alice. Her distance is going to be her rate times her time. Well, her rate is x, that's what we don't know, and her time is 10 seconds. So x times 10. For Bob, on the other hand, we can do the same thing. Bob's rate was x plus 2, and his time, just like Alice, was 10 seconds. Now, how can we relate those to the 80? Well, what we're looking at here is Bob's distance, and what we're looking at here is Alice's distance. Notice if we combine Bob's distance and Alice's distance, that is the same as the whole distance between them, which we know is 80. In other words, if we take Alice's distance plus Bob's distance, that should equal 80. Algebraically, we have Alice's distance is 10x plus Bob's distance, which is 10 times x plus 2, and that should be equal to the total distance between them, which is 80. From here, we can solve for x, and that will tell us part of our answer. So first we can distribute the 10 inside the parentheses, and we get 10x plus 10x plus 20 equals 80. Combining like terms tells us that 20x plus 20 equals 80. And then subtract 20 from each side, which tells us that 20x equals 60. And then by dividing by 20, we know that x is equal to 3. Now, what does that 3 actually tell us? Well, fortunately, we wrote down at the beginning that x is Alice's speed, and so this tells us that Alice walks at a rate of 3 feet per second. We were asked to find both her and Bob's speed, but we know Bob walks 2 feet per second faster than Alice, and therefore Bob must have walked at 5 feet per second.